calculator, get it out. If that's the one you're going to use on the exam, I still have a couple of them up here. So in the first one, if I see moles and grams, then I automatically know I got to do this first. I got to find the formula mass. So CH4. So how many carbons in that formula? 1, right? And so I'm going to multiply that 1 carbon by what? 12. That is the mass of carbon. Look on your periodic table. See, it's 12.01. Just round it to a whole number. So I will just have 12 grams. That's the contribution of carbon. But then I have 4 hydrogens. So if I have 4 hydrogens, each hydrogen weighs 1. It's 1.01 or 1.008. Just round it to a whole number. So that means that there's 1 gram for each hydrogen. So that means now that's going to contribute 4 grams. So the total number of grams in 1 mole would be 16. So this is the formula mass. So since they're equal, 14 grams of water is equal to 1 mole. Now I can set it as a unit conversion, right? Just like saying 12 eggs is a dozen. I can now use these as equal. So they can go this way or that way, depending on what my math needs are. So now if I take 3 moles of CH3, times in the line, what do you put on the bottom? Moles. The unit you start with always goes on the bottom. So moles will go on the bottom. The unit I want to get is what? Grams. So see, that's my answer. So that goes on top. So see, grams is my answer unit. It goes on top. So what do I put in front of grams? 16, because that is the formula mass. And moles is always going to get the 1. So this is where, if you do the math, 3 times 16 is 48 grams. Okay? Last step, though, significant figures do matter. So you do have to go back and check what is the number of significant figures in. I only have 1. 1 significant figure in 3. I don't use 16 because 16 you figured from the periodic table. 16 is not a measured number. 16 is like a reference number. So just always go back to the number in the problem. So 48 can't stay. What do I round 48 to? 50. Okay, so I'm going to keep the 4, but the next number is an 8, so that's going to round the 4 to a 5. So 48 becomes 50, right? So you wouldn't round it to 5. You've got to keep the 0 at the end, but remember, zeros at the end are not significant unless there's a decimal. So I'm going to keep that 0, making it 50, rounding 48 up. Next one. So 100 grams of CH4 is that equal to how many moles? As soon as you see grams and moles, you know you use that formula mass, but we already calculated it above. So it's CH4, so we don't have to redo it. We can just use that 16 grams equals 1 mole number. So here, 100 G times in the line, what goes on the bottom this time? Grams. Whatever you're given goes in the bottom in the first step. Right? Just like when we did the regular unit conversions, you see 100 grams, grams goes on the bottom, and the answer I want is moles, moles goes on top. Okay? Moles gets a 1, because see, 1 mole is equal to 16 grams. Grams then gets the 16. Okay? So I can use that, I can flip it whichever direction I need, and it's going to get my units to cancel. So now when I do this math, so 100 divided by 16 is 6.25. Last thing to do, though, look at your significant figures. It won't let me do it again already. It's really wonderful. It's gotten worse since IT came. Not saying anything. Not saying anything ever again. All right, 100, how many significant figures? 1, because there's no decimal place, right? So that means my answer has to have 1. So that means that 6.25 becomes what? 6. Okay, so 6 moles. So look at the number in the problem, only 1 significant figure, so I do have to round it. Okay, so then the bottom two. So the bottom two, when I see moles and molecules, I don't use the formula mass. I know that if I see moles and molecules or molecules and moles, you're just going to use Avogadro's number. So 3 moles of CH4. So 3 moles of CH4 times in a line. What goes on the bottom? Moles. What I'm given goes on the bottom. So moles is what I start with. So moles goes on the bottom. What goes on the top? My answer, which is molecules. Now in front of molecules, I'm going to put 6.02 times 10 to the 23rd. On moles, I'm going to put a 1. So do you see Avogadro's number? Okay. So molecules get 6.02 times 10 to the 23rd. Moles gets the 1. So when I do this, I'm going to multiply. So 3 times 6.02 times 10 to the 23rd. And I got 1.806 times 10 to the 24th. Do the math. I want you to check yourself. Can you get this number? If you can't get this number, if your answer comes up anything other than this, raise your hand. Because we'll walk through the steps on how you put it into the calculator. Don't not say anything now because you'll miss this on Tuesday, because I promise you, you have to do this on Tuesday. You will have at least 3. So you want me to walk you through it? Okay? All right. So you put in your calculator. You have the old school or you have a graphing? Okay, so you have mine. I call mine the old school calculators. They cost $10, but they do the job. So in this, here's what you put in. I want you to put in 1.06. Then I want you to hit the EE button once. Somebody thought it was EE, so they had to hit it twice. No, hit it just one time. The button says EE. Do you see it above number 7? Okay. Then you're going to go, oh, sorry, I'm doing it backwards. Sorry. Erase that. I want you to do 3 times 6.02 EE 23. And then hit equals. Okay? Is that what you got? Write yourself for the note with that. Okay? So times 10 to the is the EE button. You don't have to put any times or anything else. You just put 6.02, then the EE button, and then those two little number values come up that kind of look smaller in the upper corner. Then you put the 2, 3. You should see the 2, 3 go into that little box. Then when you hit equals, it may come up in your answer would be 1.06. And then you see the 2, 4 kind of smaller in the upper right. That's times 10 to the 24th. So when you see an answer that looks like this, 1.06, and that, do you see on your calculator, you see that little 2, 4? Sorry, 2, 4. Good grief. Right? So that little 2, 4, that's what this means. So just convert it back. So just add back in the times 10 to the. I still can't keep that though, right? 1.06 has how many significant figures? 4. So I only need what? 1, right? So 3 is just 1 significant figure. So 1.0806 rounds to 2. So this would be 2 times 10 to the 24th. You keep the exponents, okay? Don't drop the exponents off. They stay. It's the number out front that you got around. So now this one's really the big challenge, see, because you've got to put 2 exponent numbers in for this one. So 1.87 times 10 to the 25th molecules of whatever. Really doesn't matter what they are. But what am I going to put in the bottom? What unit goes on the bottom? Molecules. The unit you're given is the one that goes on the bottom. And the unit I want is moles. So moles gets what? What value does moles get? A 1. Moles always gets the 1 in these, right? Because it's always compared to grams to 1 mole or molecules to 1 mole. Molecules gets 6.02 times 10 to the 23rd. So do the math for this. got 31.06312292 moles.
So on our test, do we have to put the big version of the numbers first?
Well, I mean, I'm just putting them down so everybody knows what they should get, but you're going to end up having to round.
So like even if like the first one, if we went ahead and just put 50 as our answer, we never put 48 down.
That'd be fine. Now, unless I told you to show your work. Okay, so I got 31.06312292. Did anybody not get that? Huh? Okay, so here's the steps. Okay, I'm gonna do look, I already lost that. So I'm gonna write the steps up here so you can see. So I'm gonna put 1.87, then the EE button, then 25. Okay, if you have the old school calculator. Okay, then I'm gonna go divided by 6.02 EE23. Huh? Say it again. Yeah, so we haven't rounded there. We're not there. We're not quite there yet, but you're right. Yeah, that's what it would end up being. Okay, I just want to make sure everybody knows how to put it in the calculator, because I'm telling you, that's the reason why you get it wrong. People end up getting these wrong because they just can't remember how to put it in the calculator. So practice this. It's one of the reasons I really want you to have a calculator of your own that you can then practice as you're going through and reviewing things. But, I know $10 sometimes is impossible. All right, so 1.87 EE25 divided by 6.02 EE23 comes out. Everybody now got 31.063 whatever. Follow this right here. Follow those steps exactly, okay? So hit clear, put in 1.87 EE, see the EE button above number 7? Just hit it once, then put a 25, then divide it by, hit the divided by sign, and then hit 6.02, then hit the EE again, and then 23. Did you get it? Okay? So if it's at all challenging, whatever, put that in, and then when you're home, just try to practice it a couple of times, okay? Make sure that you feel okay, I can put this in, okay? That EE button means times 10 to the. So the next thing that you put in, only costs $10. So the next time you have to put this in, it should just be a little more familiar. I don't want it to be first thing. But 1.87 is how many significant figures? 3. So that means I do have to still round my 1.3130631292 number, so it rounds to 31.1. Okay? So I have 31.1 moles. So everybody see where the rounding comes. So remember, you go back to your number. You're not rounding by exponents. You're rounding by the number in front of the exponent. 3 significant figures, so my answer should have it.
That's the answer, right?
Correct.
Okay, because the stuff underneath it is the steps.
Right.
Okay, just making sure.
Yeah,
Okay.
that's how I got one. And what you would see on these calculators is it came out 1.806 and then a little 24. So the little 24 means times 10 to the 24.
Okay, thank you.
Okay? Okay, so the one thing that I like about the EE button is literally the EE button puts this in parentheses and this in parentheses for you. If you have a graphing calculator and you're using the little caret, the little caret up, I don't know if you remember, if you have a graphing calculator, you probably understand what I'm saying. You remember you always put your exponents in parentheses. If you don't, your math won't work because it won't keep that as a group. It tries to multiply them, and then you end up not dividing them by the right number of things. So if you have a graphing calculator and you're used to doing it the old math way, like the way the math people teach you, just make sure you use your brackets. But if you hit the EE button, it puts them in there for you, which I think is nice because then I don't have to remember to do it. Okay? All right. I will post this, right? So you know the marked up PowerPoint is posted, so you can go back and practice setting up and answering these questions. I also gave you, and I think a bunch of you picked them up, but if you didn't, there's more, just pick them up on your way out. I did do a review sheet for this exam. It is posted in Moodle, but I went ahead and printed some out just in case you forgot. So all of this first page and even onto the second page, like there's sort of examples of things you should be able to do in chapter 3. So this is like just a big hint. You're gonna have questions. They're not identical to this, but they are going to be like this, okay? And it really kind of like covers all of those topics that we did in the chapter. So one thing, remember, right? When you come, do not forget to prep your note card for Tuesday, okay? If there's things like this and you like need to like remind yourself and write the steps, how I put it in the calculator, maybe that's something that you need to write small as an example, okay? So that's where going through this, going through your notes, going through the examples, if there are things that you find that you're like, I'm never gonna remember that, those are things that you wanna put on your note card. It needs to be 4 inch by 6 inch, okay? And then you will always get a periodic table. You don't need to spend time writing down masses of elements. You always have a periodic table. But you do need to know the names and the symbols for those 30 elements. So if we've been going through naming and you're like, oh, I can't remember what that one is again, that might be something that, well, honestly, you really just need to set them out like with flashcards or something and just go over them and over them. It's only the 30 elements I gave you in chapter 1, okay? You're not going to see elements and have to know the names and formulas, the names and symbols for anything other than those 30, but those 30 you need to know, okay? All right, so where are we now? Where am I? Okay. Chapter 4, if you were in lab, so I know not everybody in this class is in lab, but if you were in lab, chapter 4 is all about organic molecules. So organic, when you think of something that's organic, you always think, well, it doesn't have pesticides, it doesn't have bioengineered molecules. Every nutrient's bioengineered, like you gotta give it up, okay? But in this, it is anything that contains carbon, okay? So this can be everything from all the nutrients we're going to talk about, carbohydrates, proteins, lipids. This can also include your molecules like ethanol, a lot of the products that are used in industry. Anything that has carbon is considered organic. Now, the ones we're going to really focus on are primarily hydrocarbons. So from this name, hydro, you think of what? Hydrogen, and carbon, carbon. So these are hydrocarbons, are molecules that are composed almost entirely of nothing but carbon and hydrogen. Carbon and hydrogen have no electronegative characteristics to them. So remember that these are two atoms that will share their covalent bonds very evenly, and this is why they are nonpolar. So remember, in sharing covalent bonds, nitrogen, oxygen, fluorine, and chlorine, those make a polar molecule. Well, if you just got carbon and hydrogen, then you're going to have a nonpolar molecule. This is why the hydrocarbons tend to be your greasy, oily, waxy type of materials. Fuels as well. So we're going to talk about sort of names of them. They're going to look sort of familiar because they are very commonly found in your fuels. And when fuels burn, they're extremely exothermic, right? So heating oil. So if you burn wood, lots of carbon atoms there. In terms of living things in the body, we have what are called lipids. So lipids are really fats and oils. On nutrition labels, they call them fats, but in reality, they really should call them lipids, and that encompasses both types, both fats and oils. We will talk about lipids in the next chapter and how they are used to build these barriers, how they're used to make things like cell membranes, how they make membraned organelles, in the cell and how they create this nice barrier to keep things in or out of compartments in living things. Okay, so this is really starting, this is kind of like the lead up to what I call the biomolecules, the biochemistry part of this course, which is really just talking about all the nutrients, how your body uses these nutrients, what these nutrients look like, what kind of chemical characteristics these nutrients have. So these are when we talk about proteins, carbohydrates, and lipids, right? Those are your 4 basic nutrient types. We'll also talk about DNA, but it's not really a big nutrient, but it's super important in the cell. So you're going to see some different structures. Some of these structures you've seen before. Some of these structures we built covalent molecules in chapter 3, but some of them are going to be kind of new. So just to introduce them, ones that should be familiar, Lewis structures, right? So see the Lewis structure down here. So a Lewis structure just uses a dash for every covalent bond. We're really going to be focusing on all single bonds. So you're not going to have a lot of double bonds in the molecules. Naming wise, we're only going to be looking at things with single bonds. So Lewis structures help you to see every single bond, every single atom. They're very exhausting to draw. Once you start getting beyond like 5 and 6 carbons, then there's lots of lines and there's lots of hydrogens. And so to try and simplify those a little, like what it shows here, so like if you did even 5 carbons in a row, you know that carbon has 4 covalent bonds. If they're all single, that means every single one of those carbons has a line up and a line down and a line to the left and right. They're all joined in one long chain. That means that if there's nothing else, there are hydrogens above every single carbon, hydrogens on each end, hydrogens below every single carbon, and that's just a 5-carbon molecule. When you get to 10, that's a lot of hydrogens. So then they said, well, let's try to simplify this, make this a little bit easier to draw. So they came up with the condensed structural formula. And if you had me in lab, you know that I said this is pretty much my favorite way to draw them, because condensed structural formulas show you how the atoms are arranged. So I could write this molecular formula. So I could say, well, this is C5H12. But you see, when you see C5H12, you're like, well, how does that go? Then you got to sit around and try and start like linking them, joining them, like figuring out how they come together. Condensed structural formula puts a carbon, tells you what's around it, then links it to the next carbon and what's around it, and the next carbon. So how would I write the condensed for this 5-carbon chain? What would that first carbon have? Does everybody see that? So the one on the left, there's a carbon with 3 hydrogens around it. Then I list the next carbon, which has how many? 2. And the next one? Next one. And then the end? So do you see the conversion? Okay. So don't think that means there's a carbon to a hydrogen to a carbon, because remember, hydrogen never has but one bond, right? So it is hydrogen. Do you notice how hydrogen's like always around the outside in the molecule? It's only ever going to have a single bond. So when you see that condensed formula, don't think that means that I have a carbon linked to a hydrogen, linked to a hydrogen, linked to a hydrogen. They don't do that. What that means is there's a carbon with 3 hydrogens single bonded, and then that first carbon's linked to a second carbon that has 2 hydrogens, and the next carbon is attached to the second carbon with 2 hydrogens. So it sort of follows along. The atoms after each of the carbons in this condensed structure tells you what's attached to that specific carbon. And those carbons are all in a chain. Then some people said, well, that's still way too much. So when we're talking about 10 carbons in a chain, instead of doing condensed structural formulas, we need to be able to draw things really fast. And so we're going to use skeletal structures. Skeletal structures only show the bonds between carbon. So it takes out, there's no symbols, there's no hydrogens listed. Even though they're there, they're not listed. So if you look at this 5-carbon group, how many carbon to carbon bonds do you see? There's 5 carbons. Count the bonds between the carbons. 4. Does everybody see that? Okay, so if I can actually highlight them, 1, 2, 3, 4. Those are carbon to carbon bonds. Do you see all the other lines are actually bonds from carbon to hydrogens? Notice that only those purple ones are actually carbon to carbon bonds. And there's like a little trick. There is, whatever the number of carbons, you'll always have one less line. Okay, so if I have 5 carbons, I only have 4 lines. If I had 10 carbons, I'd only have 9 lines. Okay, so the number of lines in a skeletal structure is always the number of carbons that you're trying to draw minus 1. So when I go to draw this skeletal structure, I use a zigzag because carbon has that tetrahedral shape, which actually, when you start making carbons in a chain, they automatically start to take on a zigzag shape. So skeletal structure for this 5 carbon chain would be 1, 2, 3, 4. Every end in a skeletal structure and every corner in a skeletal structure is a carbon. So you can kind of go back and think of them as looking like, okay, I know then there's a carbon here, 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 and here. So do you see that there's like 5 red dots? Those represent the carbon. So in a skeletal structure, the end of the zigzag and every corner in the zigzag is a carbon. Any place that lines come together, that's a carbon. So just to, oh, you got it. All right. So we are going to be focusing primarily on what they call alkanes. Alkanes are when you have chains of carbon that only have single bonds. So all the bonds between the carbons, they're always going to have just single bonds. So when they're just pure hydrocarbons, and they are all single bonds, they will call them saturated. So I remember saturated means it's all single. So saturated and single, the S's. Saturated, it has like as many hydrogens as it possibly can have. So it's saturated with hydrogens. So that's the maximum number of hydrogens by having them as all single bonds. So in the naming, so the first 4 carbons in the chain, or the first 4 numbers of carbons, they really have more of a historical significance, which is where they've been kept, which is really strange because I would think that the fancy naming people would have said, no, we're going to like a common name, like a consistent name that fits, but no. So if there is just a single carbon in a molecule, like CH4, so remember we actually drew CH4. We did the Lewis structure. This was one of our covalent molecule examples. They call this, I told you it was carbon tetrahydride, right? Because if we named it according to its binary name, that's what it would be. But when we're talking about it from an organic standpoint, instead of calling it that, they call it methane. So a single carbon with 4 hydrogens is a methane molecule. If there's 2 carbons, then those 2 carbons are connected side to side. They're going to have 3 hydrogens on each. So notice the molecular formula and then the condensed structure. Condensed structure shows you it's a carbon with 3 hydrogens linked to a carbon with 3 hydrogens. They call that ethane. So it doesn't follow a di or a bi or any kind of naming like that. It's ethane. 3 in a row is called propane. So that is where you have a carbon with 3 hydrogens linked to a carbon with 2 hydrogens linked to a carbon with 3 hydrogens. See the condensed structure above. And then the fourth. The fourth is the other odd one in terms of its name. They call it butane. So butane is when you have 4 carbons in a chain, total of 10 hydrogens. There's a hydrogen above, below, and on the ends with all of those carbons. Well, methane, I can tell you a couple of things about these in terms of their naming. Methane, this is natural gas. Okay, so methane is commonly used as a heating source. If you live in the city and you have city gas, it's methane. Okay, so you might have it like we finally got a gas stove. Like I've never had a gas stove in my life. I used to have the coils, but now I have a gas stove. We've really moved up. So the gas, since we live in the city, so the gas that pipes into our gas stove is methane. If you live out in the country though, then you have LP gas. Okay, so you might have like a big silver, what I always call the silver bullet in the backyard. I don't know if you've ever seen like the propane tanks, and like if you're driving out in the country and you drive by and you see the propane tanks in people's backyards, that's liquid propane. Okay, so methane is too difficult to transfer. It's easy to pipe through a pipe, but it's too difficult for trucks to transfer. And that's why out in the city, if they have gas, then they're going to use liquid propane. So they call it LP, which just stands for liquid propane. If you have like a gas grill and you buy like the 20-pound tanks, that's propane. So it's much safer. You can't tank methane. It doesn't become a liquid. But if you put pressure on propane, it'll convert into a liquid. So it's pretty convenient. Then butane. Where have you seen butane? Yeah, a lighter. A Bic lighter is a butane lighter. And so you can actually see the liquid in there. That is because the butane, normally it would be a gas, but under pressure, it forms a liquid. When you push the little lever down, it releases the pressure and the liquid converts to gas and comes out the little hole. So you put a spark and that ignites that fuel, and now you've got a little light. Okay, so then that's a lighter. If we continue going down, octane. Where have you seen octane? What's an octane rating? That's a rating on, I buy 87, but some people like to have 92. Gasoline. So this is a component found in gasoline. So notice all these are fuels. Methane, propane, butane, gasoline, all of these are found in fuels. Methane, ethane, propane, butane, those are ones that you really just have to like practice and look at and name and look at them and name them again and maybe write them on your note card if you can't keep it straight. But note from 5 going down, these follow what? Shapes, right? A pentagon, a hexagon, a heptagon, an octagon. So the name in these tell you the number of carbons and they match like what the geometry is. Because it would look like this, and that looks like a single bond. Okay, so they really, and like even propane looks kind of ridiculous, right? So propane looks almost like a little arrow. So I really don't start using skeletal structures until I'm into 4 and 5, because it really is kind of odd looking. Yeah, because then it would literally, that looks, to me, it looks like a single bond. So it'd be like, there'd be a carbon on each side, but there's no points. There's no bend to it. So they don't typically, and yeah, so methane would be like a dot. So that would look even stranger. So that's why they don't really do skeletal structures until you get like into the 5, 6, 7, because it just gets so much easier. But notice with those, if you're counting like nonane, you can count 8 lines in the zigzag. Okay? Because those are the bonds between carbons. And when you get up into the octane, nonane, decane numbers, it is really convenient to draw skeletal structures. You just got to make sure you go back and count your lines. Okay? Decane should have 9 lines. Octane should have 7 lines. It's always 1 less than the number of carbons in the molecule. Okay? So that's just an easy sort of way to check yourself. So here's some examples, and these ones show your skeletal structures, and you see why hexadecane, the skeletal structure, is really convenient. That's a lot of zigzags. Look at wax, candle wax, paraffin. That's 31 carbons. Can you imagine going C, bond up, bond down, hydrogens, right? So you would end up having 64 hydrogens. So this would take you a while. So this is where they said, wait, we need something simpler. Not even condensed is convenient. But again, notice all of these gases. Diesel fuel, even candle wax. So when you burn a candle, you know that the wax does burn. Okay? It burns really slow because it's super, super big. Okay? It's a huge number of carbons. It still burns, right? So you notice like it doesn't just stay there. The wax disappears too. Well, the wax does burn. It just burns really slow because it's such a big molecule. Okay? One other way that you're going to see these. You are going to see carbons that not only are in a chain, but they can also form a ring. If you see a ring, then you are going to use cyclo, okay? So I think of cyclo as looking kind of like a circle, right? So cyclo is more circle in name, and that's really what it's telling you, is that it's telling you that there is a ring structure. The reason we can do this is because carbon does these 4 single bonds. So carbon can form bonds and rotate around and be able to reconnect. I will tell you that you don't find these in nature, cyclopropane and cyclobutane. And the reason is remember that the tetrahedral is like 109 degrees. Those are way smaller than 109 degrees, okay? So cyclopropane is only like a 60-degree angle. The bond angles are really tight. Carbon doesn't like that. So that's like cramming electron pairs into a really tight space. So you don't see those in nature, but you do see these. Cyclopentane, cyclohexane. Cyclooctane is probably the only other one that you'll see. And if I use this, I'm going to use the structure draw, because I, for the life of me, cannot draw an 8-sided structure. It ends up looking very strange. Like some lines are really long, some lines are really short. So I have like the insert structure. And I'm like, there, perfect. Okay, so cyclooctane, those would be the only ones. You name those by the number of carbons in the ring. So see the one that looks like a little house? So that one is cyclopentane, a 5-membered ring. Notice then the one that's 6, that is cyclohexane. And cyclooctane, isn't a stop sign an 8-sided shape? Not a 6, it's an 8, isn't it? Okay, yeah. Okay, because that's why I was like, I still can't draw it though. I can recognize it when I have to pass a driver test. Okay, so you will see this sometimes. Okay, so those are really the 3, cyclopentane, cyclohexane, cyclooctane, that you might see. So if you just see this, so if we say CH3, CH2, 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 CH3, that example, what would you call this? It is just a chain of 5, so you would call this, 5 would be what? Pent, so this is pentane. Pent because it's 5 carbons in the chain, A-N-E because they're all single bonds. All of your names are going to end in A-N-E in this class. If you really like doing this, you could take a 2-semester class of organic chemistry, and then you get to names all kinds of stuff. No. It was okay. It was okay. It's just really like a lot of like, you practice all this naming, and then you just do a lot of practicing with like reactions that they do. But it's not bad. All right, it's just repetitive. That's what I found. So that's pentane. All right. But what if I have these 5 carbons, but they're not all just in a chain? So what if I have this? And this, I would say, this is a condensed molecular formula. So in this one, I have CH3CH, CH2, CH3, and then hanging off of that second carbon, I have a CH3. So if you count, that's still 5 carbons, yes, agreed? That's still 12 hydrogens, okay? Just like what pentane. So these are actually, they have the same formula, but they're set up differently, but they're not the same name. You agree that they don't look like the same molecule? Okay, so now I've got to be able to name this to tell them apart. So this is where the International Union of Pure and Applied Chemistry, they came in and said, well, we're going to have rigid naming rules. And if you've tried to do any of your chapter 4 stuff, you're like, geez, here's the rigid naming rules. Okay, so like legit, just follow these 4 steps every single time. Okay. So the first step in naming any branched chain, and by branched I mean it's not just a straight chain, that there's something hanging off that's not a hydrogen. You always find and name the longest continuous chain of carbon atoms, and they do not have to be straight in a line. I'm saying they're just connected. So you're trying to find the longest connected chain of carbon in a molecule. So in our example, CH3, CH, CH2, CH3, CH3. What is the longest continuous chain? 4. Okay, so then what I tell you to do, circle it. Okay, and then name that. That ends up becoming the last name in the name. Okay, like they say the parent name, so it's sort of like your surname. So this ends up being what? What's a 4 carbon? Butane. So this is now butane. And I always just put it over on the right because I know now that's my last name. Then step 2. I have to name anything that's not hydrogen that is attached to my chain. So do you see that there's all these CHs on the chain? You don't have to name any of those. You're done with those, okay? Anything you circle and name, you're done with it. You're just looking for anything you haven't circled. And that's why I circle them, because that way I don't forget things. I don't like leave a branched piece off just because I didn't circle them. So in this, now, favorite life. What's my chain that's hanging off? A CH3. So we know that a single carbon CH4 is what? Methane, right? So a single carbon CH4 is methane. But if it's a group hanging off, instead of saying methane, which makes me think of a single CH4, to indicate it's hanging, they call it a methyl. So they still use meth because it's a single carbon, but instead of ANE, they just drop that and put a YL. So notice the YL on all of these. So this is a methyl. So now, is there anything not circled? No. So I've now actually identified all parts of my molecule. Now I can do step 3. Okay? So don't go on to step 3 until you've named them all. Okay? So if I had, and you can have like multiple ones hanging off of the chain, you got to name everything that's not hydrogen that's hanging off of your longest chain. Step 3, I'm going to number my chain from one end or the other. I want to give my hanging group the lowest number possible. So if I'm going to either start numbering from the left or from the right, and I find it's easiest, start from one end and count how many carbons till you get to a hanging group. Start from the other end, count how many carbons till you get to the hanging group, and that helps you figure out which side to number from. So based on this, which side do I number from? The left. Does everybody see that? Because that will put my methyl on carbon number 2. So this one will be 1, 2, 3, and 4. So that means this is 2-methyl. That number 2 tells me which carbon the methyl's hanging off. It doesn't mean I have 2 methyls. It tells me which carbon on the chain it's hanging off of. So now this becomes 2-methylbutane. It's like terrible looking. That's an M. Okay, so that is 2-methylbutane. If you have more than one hanging group, always name all the hanging groups, then do the numbering. If you have more than one, then step 4 comes into play. Step 4 says you have to list the hanging groups alphabetically. Okay, so if you had like a bromine and a chlorine, you'd put bromo first, irregardless of where they are on the chain. So like bromine might be 3, chlorine might be 1, but I'm still going to list bromine first because it's alphabetical. Okay? All right, let's practice, because that's really the only way. Hold on, and I lost it again. Next. Here. So in this one is kind of simplified. I didn't put the hydrogens because I think it actually makes it easier to look at just the carbons. Sometimes don't let the hydrogens like throw you. So this top one, find the longest carbon chain. Tell me, what do you see? Okay, 6. Anybody see any more? And remember, we're looking in a chain. So I've got 6 this way. Yes, agreed. Notice also, though, I could go like this. Would this be wrong? See that? That's 6. And so that's why I say, like, so could I do this? Yeah, that's 6 too. Okay, so sometimes there'll be multiple ways. Pick one. Okay, so for simplicity, we'll just go straight in a line. So we'll just do it this way. So that means this is a hexane, right? So a 6 carbon tells me that it's a hexane. Now I'm going to name the groups. So here is a C, a single C. It would have 3 hydrogen on it, so that would make this a methyl, right? Remember, a single carbon hanging off. But now this one coming down here, that is a little different because that's a 2 carbon group. So that would be like a CH2, CH3. So that would be what? Ethyl, right? So remember we said 1 carbon is methane, so that would be methyl. 2 carbons would be ethane, so this is an ethyl, right? So anything hanging off of the chain, just make sure you add the YL if it's a hydrocarbon. So now, I've circled everything, right? And that's why I do it, so that I can see, okay, I've handled everything. I haven't left anything out. So now I got a number. So check from each side, which side do I want to start numbering? From the right. So does everybody see? If I go from the right, the methyl is a 2. If I go from the left, the ethyl is a 3. So I would want to start in number 1, 2, 3, 4, 5, 6. Okay? That's all I'm doing is just numbering the longest chain. So that means my methyl is now a 2-methyl and my ethyl is a 4. Okay? So the number you put in front of the hanging group is just telling you which carbon it's hanging off of. So now since I have 2 of these, the rule is I have to list them alphabetically. So which do I write first? So I put 4 ethyl, 2 methyl hexane. Now the IUPAC guys, gals, whoever they are, the group that decided all this mess, they also decided that they didn't want any spaces because they were concerned that spaces would make you think it was a different name. So instead of spaces, see how there's like a space between 4 and ethyl, a space between ethyl and 2? So instead of spaces, they put dashes. I really don't care. I am not going to mark it wrong if you do not put those dashes in, but they do. Okay, so you will see that if you go in, you're doing your mastering stuff, you will see those dashes put in. All it's doing is so that it's like all one word. And in fact, methyl and hexane, so the parent name and the last, well, the closest non-hydrogen hanging group, in our case, we had to put methyl in that spot. Those end up being all one word. So there's no space between methyl and hexane. So it just becomes methyl hexane. Okay? So that's like the fancy way that you would actually write it. I really don't care. Okay? You're not numbering according to the alphabet. You're numbering to give the lowest number combination possible. Okay? So if I numbered, so let me show you. If I numbered from the other side, if I said this is carbon 1, 2, 3, 4, 5, 6, right? So I'm going to number from one side or the other. What would ethyl be now? 3. But what would methyl be? 5. So do you agree that 2 and 4 is lower than 3 and 5? That's why. Okay? That's why I say just look at the chain and kind of like count in how many carbons before I get to a hanging group. Whichever one has the hanging group closer, that's the side you number from. It has nothing to do with what the name is. Like that could be a chlorine or a fluorine or it could be a propyl. It doesn't matter. Right. You're just looking at, okay, where are my groups hanging off of my chain? I want to give them the lowest number possible. So look at the bottom one. So again, this one's really just showing you kind of like the carbon skeleton. I didn't put the hydrogens in just to help you kind of looking at the chain. What is the longest number of carbons that you can find? Does everybody see that? So you can go like this. Does not have to be in a row. So I'm just looking for the longest chain of carbons. So they could go like a little zigzag stair step. Just find the longest chain of carbons. So 8 makes this a octane. So remember, 8 is oct. So this is the chain. Now I've named all of that. So I'm done with that. So is there anything that's not in the circle? What? There is just a single carbon. And that single carbon then is a what? Then this is a methyl. So now, do I number from the left or from that upper right? Upper right. Do you see that if you start from the ends and count, do you see if I start from the area right underneath the word octane, then my methyl is on carbon number 3? If I started from the other side, it'd be 1, 2, 3, 4, 5, 6. So that's why I start from the side over here. This will be 1, 2, 3, 4, 5, 6, 7, 8. You don't have to number the entire thing. Like literally you can just number until you get to your hanging groups. But that means that now my methyl is 3. There's only one, so I just throw this up front. 3 methyl octane. Okay? And I do put a dash after the 3 because that way there's no space. Okay? So you're really not going to see them written that way. You are going to see them written, really now. So you are going to see them I despise you. This way. Okay? This is a Lewis structure. There's 3 of them. So take a minute. I want you to name all 3 of these following the steps. Okay? Follow the steps. You should have them. They should be in your PowerPoint. I didn't change any of these ones. All right, so the first one, what's the longest carbon chain? Butane. So C4, and it would not be wrong if you had gone across and down. This would still be the same. It's still butane. So this is butane. And then this hanging off is a methyl. A single carbon is a methyl. So now if I'm going to number, do I number from the left or number from the bottom right? Because that would be 1, 2, 3, 4. So that's going to give me a 2. So this is 2 methyl butane. Number 2 just tells you which carbon that methyl is hanging off on the butane. Going across to the other side, longest carbon chain. 6. So does everybody see this? Make sure that you kind of like go through. So notice going across and down is 6. If I just go straight across, that's only 5. Okay, so 6 makes this a hexane. All right, so 1 is ethane, 2 is 1 is methane, 2 is ethane, 3 is propane, 4 is butane. But then it goes pentane, hexane, heptane, octane, nonane, donane, decane, which are all based on geometric shapes. So then I got to name this. This is a methyl. It's a hexane. So see, go follow down. See the way that I circled? Well, but see, so pentane is too small. You want to always find the longest carbon chain. Okay? Am I done? Hydrogen, 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 hydrogen. But do you see this? What is that? Chloro. Okay? So the only other ones you're going to see besides like methyl and ethyl is that you will see the halogens. And the reason why the halogens are used is because the halogens only form how many bonds? 1. They're in group 7. They never form more than a single bond. So literally, I could take fluorine, chlorine, bromine, and iodine and replace it for any hydrogen in a molecule. And if it's there, you have to name it. Fluorine becomes fluoro. Chlorine becomes chloro. Bromine becomes bromo. It's like you use the first part of the name and an O. Okay, so that's a chloro. So now I've named everything. Do you see that everything else is just H? So you don't have to name those. Right? Hydrogens are like assumed that they're there. So now I have to number. Which side do I number from? The upper left. Why? Because chlorine's on that very first carbon. So this would be carbon 1, 2, 3, 4, 5, 6. So that makes my chloro a 1 chloro, and it makes my methyl a 4 methyl. Because chlorine's on the first carbon over there, so it's definitely where I would start, right? So in the first one, see where the bottom, that if I count up and to the right, then that's 1, 2, 3, 4. If I started on the left and came down, that would put my methyl as a 3. So I want the lowest possible number on any non-hydrogen hanging groups. So then that way it just makes it consistent so that you know. Okay? Bottom one, longest carbon chain. Yes. Okay, everybody got 7. Now notice in this one too, yes, I could go straight across, but no, it would not be wrong if you went like this. Do you see that's still 7? Okay, and even if I went like this, do you see that's still 7? It wouldn't change. Remember, single bonds, they rotate. So these could rotate. I could actually like flip them around, still make it look like this, right? So just for the ease, we'll go this way. So now I've got to, so that means, what's this name? This is a heptane, right? Hexane, heptane, octane. So just make sure you go back over those number prefixes, what those shapes mean. So 7 is a heptane. So this C is what? This is a methyl. So a single carbon hanging off is always a methyl. So this, though, is a 2-carbon group hanging off. So this is a ethyl. Anything else? There is a bromo. Everybody catch that one? So that's what I do is after I finish, I like look all the way around and I'm like, is there anything hanging off that's not hydrogen that I have not circled? Okay? And I'll tell you, chlorine sometimes is tricky because it looks like a carbon, right? So people don't like, they like ignore it. Then they go, oh, I didn't even see that. Same thing. Okay? So now I got a number. So you tell me, which side do I number from? The left. Does everybody understand why? So see, from the left, my methyl is a what? 2. If I went from the right, my ethyl would be a 3. So that tells me to start from this side. So I just kind of go in from each side, and wherever I get the first, this is 2, 3, 4, 5, 6, and then 7. So that means my methyl is a 2 methyl, my bromo is a 3 bromo, and my ethyl is a 5. That's all the number is. So that number tells you where that hanging group is. Last step, what do I write first? Bromo. So I have 3 dash bromo dash 5 dash ethyl dash 2 methyl heptane.
So will the bromo, chloro, and everything, will that always come before the ethyl and the methyl?
It's listed alphabetically, B, then E, then M, okay? So it doesn't matter what they are, okay? Right, so like in lab yesterday, I had them build a chiral molecule. We haven't even talked about that, but I said, this is bromo, chloro, fluoro, methane. And everybody looked at me like I was a crazy person. But bromo comes before chloro, comes before fluoro, because it's just alphabetical, okay? So it doesn't matter what your hanging groups are or where your hanging groups are on the chain. List them alphabetical. So notice this is not in order by number, which, like, yeah, that's how I would have done it, but no. That's not what they said. They said, no, list everything alphabetical. Say, I can't. Yes. So you're saying, like, if your longest chain, you had done it differently, it still would have been exactly the same. Okay? And so you can try that, but it should be. Okay? The only other rule I would tell you to do is always make sure your longest carbon chain has your non-hydrogen groups attached to it. Okay? So that's always like the best option, because if you didn't, like, there was one example in lab that we did where there was a chlorine, and so you could draw a ring of 3, but if you don't connect it to the chlorine, then it adds a level of complexity to try and name it. So always make sure that your longest chain, all your hanging groups will hang off of it. Okay, so what if you see a skeletal structure? So this throws people too. So when you see a skeletal structure, you got a couple of options. If you were me, you could just go put dots to represent carbons. So how many dots in that first one? Nope, 6. Right? So remember 1, 2, 3, 4, 5, 6. So that makes this a what? hexane. So boom, now you've already named the longest carbon chain. So then this is a chloro, and it's hanging off of carbon number 2. Done. 2-chlorohexane. Yep. Thought it was going to be way harder, didn't you? 2-chlorohexane. Okay, now what about the one below? Nope. Nope. Nope.
No.
Nope. Nope. 6. There are 6. Okay, so look. So the 6, 1, 2, 3, 4, 5, 6. Why is that last one not? That is the bond to the chlorine. Okay, so look at that one closely because people jack that up all the time. Okay, so see where the line comes to the last chlorine on the right? That's the bond from the little green carbon on the right down to the chlorine. Okay, so if it's 6, this is still a, yep, hexane, 6, hexane. That means that this is a chloro, and this is a, which way are you going to number from? Left or right? Right, so the first one is a 1 and a 2. Do you see that that's hanging off of the first green dot, second green dot? But now, instead of saying 1 chloro, 2 chloro, when you have the 2 of the same hanging groups, you can put them together and call it di. So you can put them together. So this is dichloro. What do I put in front? I still have to use the numbers. So this would be 1, 2 dash dichloro. Okay, that seems a little redundant, I know. But they still want, so if you have 2 chlorines, you're going to put 2 numbers in front. If I had a try, I'd put 3 numbers in front. Okay? So that's the part that I see people make like common mistakes is when they see a line, they go, oh, that's a carbon. But if the line is going to a halogen, then that's just the bond to the chlorine, fluorine, bromine, or iodine. What about the one up here? How many carbons? First find that out. How many carbons? How many carbons total? Nope. Upper right. Nope. Okay, I want you to put a dot on every corner and every end. 10. See if you can find 10.
Oh, I thought you meant the longest.
No, I was just asking total. How many carbons total? Okay, looking at carbons total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, because none of those lines are attached to a halogen. So those means on the end are carbons. Okay, if there's a halogen, then it's a bond to a halogen. Say that again.
I have 11. We have a different one.
Oh, I changed. Oh yeah, that I changed it because I was tired of doing. Sorry. So you got 11. Then you're right. There's 11. I think I had taken one line off. I was trying to. I had some similar names, and I was like, I don't want to keep using this name, so I changed some of mine. Okay. So now tell me longest carbon chain. On I guess on this one. You can practice yours at home. What is this one? Huh? It is 1, 2, 3, 4, 5, 6, 7. So this is a heptane. So now, what are these little lines sticking up? Those are methyls. This is a methyl, methyl, methyl. Which way do you number from? From the right. So you notice that your first methyl from the right would be on carbon number 2. First methyl from the left wouldn't be until carbon number 4. That tells me I got a number from the right. So this is 1, 2, 3, 4, 5, 6, 7. So take the time to number them, because sometimes when you number them, you'll figure out you've named it wrong. I'll tell you that, like I've done that. And like, oh, wait. Okay, so the first methyl I come to is on a 2. The second methyl is on a 3. The third methyl is on 4. Okay, but since they're all methyls, I can group them together and call it a trimethyl. So it is 2, 3, 4 dash trimethyl heptane. So those numbers tell you where each methyl's hanging off. I want you to practice this last one. Okay? So you can practice those other ones. So what do you do if you see something like this? And this is different than yours, what's in your thing, because I realized I only had one cyclo on my example, and I was like, okay, what do you do here? Tap the red one. What do I name it by? Nope. This is called what? Cyclohexane, right? So when you have a ring, you name it by the ring. Cyclohexane. And that takes care of all of the things in the ring. So then anything hanging off of the ring that's not hydrogen, I have to name. So that means I got to name what? This is a CH2CH3. This is an ethyl. There's only one. So if you have a ring and there's only one, where would I start numbering? At the hanging group, right? Because it would make it a 1. So that would be like, it wouldn't matter. It's going to be on the first one because you always want to have your hanging group with the lowest number. So this one would just be 1 ethyl cyclohexane. Okay? All right, so I will quit there. Now, if you look at your review sheet, everything on the first page we've talked about. Everything on the second page down to chapter 4 we've talked about. And in chapter 4, we have done all the naming. So 1, 2, 3, 4, 5, 6 lines in, be able to name ring structures with branches and alkyl halides, which is just the halogens. So those ones, all of this we will cover on exam 3. Okay, so see where the line is? So if you're looking at this review, 1, 2, 3, 4, 5, 6 lines down, just put a little mark. Everything above is exam 2. Everything below will be exam 3. No functional group stuff. I'm not going to make you draw them because we haven't talked about that. Well, I haven't made you draw them yet. So on chapter 4, count down 6 lines and draw a line. Okay. So drawing a line underneath, be able to name ring structures. Okay. See where that is? So that'll be like the stop point for you. So there is going to be a lot of questions on chapter 3. Because I didn't get that far into chapter